Yes.
All right. So let's look at the homework for today. How did the homework go? Easy?
Take a long time.
All right, so harder than last time, but you felt like you were a little bit better? Okay, good. That's the way it's supposed to feel before your world ends. It's gonna be so good. And what were you begging about, Clancy?
No homework over Labor Day?
That's this weekend?
Yeah.
Well, you have tomorrow, Saturday, Sunday. You got multiple days before Labor Day, right?
Well, I mean, you're not wrong,
What's the rationale for this?
It's nice to not have any homework at all. Ever.
What do you mean ever? Wouldn't you think less of me if I didn't give you homework?
I would not think less of you at all.
All right, we'll see how well people participate in class today, and then I'll take last minute groveling. We'll see what happens. So this is what you did for today, right? This guy? Okay. Let's see if I can figure it out.
I don't think we can see your screen, just so you know.
Well, how's that my problem?
It's not. I'm just letting you know.
I'm just letting you know. We can't see your screen. Yeah, I am recording. All right, you guys can see the screen now?
Yep.
Okay. Let me just triple check I'm recording. Yes, I am. Better safe than sorry. All right, number one, product is a list of symbols without repetition. So they're guaranteeing the SOS1 and SOS2 are flat lists of symbols, not S lists, right? Flat lists of symbols. And they return a list of two lists that represent the Cartesian product of SOS1 and SOS2. The two lists may appear in any order. So the product of ABC and XY will be AX, AY, BX, BY, CX, CY. All right, so we're creating two lists out of each element of the first list with each element of the second list. All right, so first thing that pops out here is you probably want a helper function, right? So we can maybe create a function that, given a list and a symbol, creates a bunch of two lists given that symbol. That would be a nice helpful one for this, right? So we'll call this guy product helper. Why is that pushed over like that? Product helper to be a lambda. That's going to take in a symbol and a list of symbols. All right, and we want to go through every element in that list of symbols and create a to list with that element with S. So can't I map over my list of symbols? I thought maybe. Oh, there it is. Didn't I make it bigger before? And it went back? Is that good? All right. So to test this, we'll say produce. It's product helper, right? And maybe we'll do A and xy. Way to go, Clancy. You're really living up to this whole no homework thing.
My bad.
All right, so this function here will map this function. That is a function that takes a single parameter and creates a list out of S, whatever S was, and that single parameter. We're mapping that across list of symbols. Now, again, this uses map, which can be a little complicated. So let's write this in a non-map version as well. All right, because remember, the way map does is it says, I'm going to apply this function to every individual element of that list. That's what map does. So if I apply this function to each element of this, I'm going to apply it to the X, then I'm going to apply it to the Y. And what I'm doing is I'm creating a list out of whatever S is and the X, whatever S is and the Y, and returning that as a list. Okay, so when you walk through it, it makes some pretty good sense, but like I kind of warned last time, is it's easy to fall prey to this idea that, oh, I'm just going to use map for everything, all right? You never actually have to ever use map. It's just helpful sometimes. But let's go ahead and let's look at a second version of this guy that does not use map. And we'll see we have our same pattern as before, right? So we'll define product helper 2 to be a lambda that takes a S and a list of symbols. And then we'll ask the question, if null LOS, then return the empty list, else cons the list containing S and the car of LOS onto product helper 2, passing it S and the cooter of LOS. All right, that makes sense? So I'm guessing for most of you right now, that's a more comfortable function. And that's okay. This can always be a more comfortable function because this actually follows this idea that I've been saying that, you know, we see the same patterns over and over again. You're building a list. How do we do that? We construct a list. You're adding some stuff. How do we do that? We add some stuff. But if we have multiple S lists and we have to sum things up across these multiple lists, then you know we're going to sum the result of multiple calls. All right, so never feel like you have to use map. But I do think map is good practice from the perspective of really starting to think about lambdas as unnamed functions, where you can take this function, and that function doesn't have to be doesn't have to have a name. We can just apply that function to every element of this list. That's what map does, and it produces for you a list containing the result in that function for every element of that list. That's what it gives you. All right, so whenever you have a list that needs to be manipulated, producing a new list, sometimes map might be worth considering. But if it just puts you in an uncomfortable position right now where it's hard to think through map and you have enough things to worry about with recursion and stuff like that, that's fine. You never have to use it. So I'll usually show you both versions as we go through it. But in any case, we have a nice little helper now that will go through, and both of them end up doing the same thing and will give me a list of elements that are the two-list combination of a symbol and every element in the list of symbols. So far, so good? Okay, so then what we need to do is we'll actually have our product function define product. That's the name of it, right? Product. To be a lambda that's going to take in a SOS1, SOS2. that what it took? Just 2 things? All right. And then what we want to do is we want to call product helper on each of the elements of SOS1 with all of the elements of SOS2, right? And each time we call product helper, it's going to give us a list of 2 lists. And what do we want to do with that list of 2 lists? Because ultimately, we want to have a big single list of a bunch of 2 lists, not a list of lists of 2 lists. So we might think that, okay, maybe I'm going to use cons here. So let's start off with that. You know, so we're going to go down a little bit of a bad path and get a, you know, like all the stuff is there that I want, but it's not quite where I want to be. That's probably something that a lot of you bumped into as you were doing this one. So we'll ask our usual question. If null SOS1, we'll just boil down to the empty list. Otherwise, we're going to cons the result of product helper on the car of SOS1 and the entire SOS2 onto whatever's returned by product for the cooter of SOS1 and all of SOS2. All right. And then when we test this, we might say product, what was it, like AB, and then XYZ. All right, and we see that we end up with a list of lists of 2 lists. Okay, but all the stuff is there. Looks good-ish, right? Okay, so what can I do? And this is the result of how cons works, right? Cons says, I'm gonna take this element and make it the first element of a new list. What do we want to use instead of cons here?
Append.
Append. So append will glue a bunch of lists together for us, giving us our list of 2 lists. All right, I think is that what it's supposed to do right there? Okay, so a couple things to, I mean, probably the real thing to focus in on there. I'm actually not even sure why they said it had to be a, you know, that we could assume that the list of symbols here were unique. I mean, it would still work even if they weren't unique characters you just have, but whatever. The biggest thing here is to kind of get you into this idea of, oh, append can solve some interesting problems for me. That ability to glue lists together without us having to cons lists in front of lists. Because then what we would need to do is, I think was the last homework assignment, when you wrote flatten, or did we write flatten in one of those? Ever written flatten? Are you lying? Oh, yeah, yeah, here's flatten. Up, which have we written up yet? Okay. Yeah, so we can undo the list of lists, right? You know, that's what up does, is it takes away one layer of list across all the elements, but better to build it right the first time than to undo it. All right, so questions about product. Go ahead.
I just have a question. Just like, I was trying to figure out how math would work in this case, since we have 2 lists. Like, which function would you use to map across the other list? Like, how would that work, since map can only take 1?
Well, map only takes 1 element. So the way I used map here is with my helper, I passed it a single symbol and the list that I was going to map across. And then the function I mapped across there took in each element from my list of symbols, but I hard-coded the S in here. So I took advantage of this being a helper function that has access to this local variable called S. Yeah, because I couldn't use both. You're right. You know, map allows you to have one input, and that makes things a little bit tougher, but you can pull it off.
So is that like the workaround you're talking
No, there's actually something called streams in Scheme, which we actually probably won't get to, that will actually allow you to kind of create something like map, but for things that have more than one input. But at that point, you know, things start getting, I mean, one of the arguments for why Scheme is good for what we're doing is it's such like a simple language. I realize it's still kind of confusing, complicated, like a puzzle-y type thing, but there's so little to it that you're always kind of using the same tools. So the second you start looking for ways to like overcomplicate things, you're probably chasing something that, not that it's uninteresting, but maybe not all that helpful. You know, it's completely reasonable for map to sometimes just not be the best tool for the job. You know, yeah, like I wish it could do it, but I got two things to deal with here. Map doesn't do that. So, and I think that would be the preferred. Like, in fact, I would say in general for the class, if map currently makes you pretty uncomfortable, just don't use it. You know, sometimes it gives you like these shockingly easy answers to things just because of the nature of map. But what map's ultimately doing is something that you would have basically written into your solution otherwise. So don't get caught up on this guy. But it is kind of a cool function, and it's not something that's just part of Scheme. Lambda functions actually exist in most modern programming languages. Python supports lambdas, Swift supports lambdas, C# supports lambdas. The latest version of Java also supports lambdas, and they also have map in those that allows you to map across an array and things like that. So, you know, this concept of applying a function to each element of a collection is a broader concept that's worth becoming comfortable with, but isn't a deal breaker for us in here. All right, other questions about product? All right. Filter in takes a predicate. What's a predicate again? Okay, so function that takes in one parameter and produces an answer of true or false. So a Boolean expression, what a predicate is. Realistically, it's probably asking, is something something else? Am I looking at a number? Am I looking at a list? Is it the empty list? Those kind of things. It's the things that typically naming convention have the little question marks at the end of them. All right, but that's what this predicate thing is here. And list is a list. So return the list of those elements in the list that satisfy the predicate pred. All right, so, excuse me. List of those elements in list that satisfy the predicate pred. So it's called filter in. It's going to take in a predicate and a list, and it's going to return this guy for number. A is not a number. 2 is a number. The list 1, 3 is not a number. B is not a number. 7 is a number. So that's why we get the 2 and the 7. Okay. Actually, the map works for this one too. Yeah. So we'll write a couple of versions of this one too. Filter in. Filter, did I spell it right? Can I see? Filter
Looks
in.
good.
Way to be on top of things. Predicate and a list. And what I can do is I can map a lambda that takes an x, and we can say if pred x else empty list. We'll map that across our list. So that should give me a collection of elements or empty lists. And then what I'll do is I'll map again. Actually, would I map again? What happens if I just don't have an else to this? I wonder what map does if nothing is returned. I think it probably gives you a null value. A213B7. Filter in number 213B7. Yeah, it requires a second element. So if I give it that second element for the else, now it's going to give me a list that contains empty lists for everything else. But what I really wanted to do is, oh, does that work? I wanted to append all those together to give me my final answer. Yeah, more trouble than it's worth. We're forcing the map on that. All right. So this one's really a pretty easy one. So we'll say if null list, so if we're out of stuff, right, we'll boil down to our empty list. Otherwise, we'll ask the question if, and really we could have done this as a cond. Maybe a lot of you did it as a cond. That's okay. So I'll actually write it both ways just so you can see the comparison. So I'll say, if I'm in this if here, I know that it's not the empty list. So I'll say if pred on the car of my list, if that's a true statement, then I'll cons car of my list onto whatever filter in, passing it pred and cooter of my list returns. Else, I'll just call filter in pred cooter of my list, because I'm not consing anything on because it doesn't belong in my answer. So there's my 2 and my 7. And if you want to see this guy in a cond, call this filter in 2. So there's one of the things. So this is the cond version of that where, you do have to make sure you check for null first so that, you survive that. Otherwise, you just have the 3 different things. I'm not sure either one's better or worse than the other one. This probably looks a little cleaner. All right, questions about that one? I didn't feel like a 2-star, did it?
What if you were to use EQ question mark for the if statement for the predicate? Like if you did if predicate or equals predicate and then the car of the list, would that change anything?
Well, if you're going to see if it's equal to it, you need to check to see if it's equal to a real thing. So if I'm going to use EQ question mark, this guy, I would have to compare it to, I think it's true, like that. So now instead of just applying, because remember, an if statement looks for a Boolean expression. A Boolean expression is any expression that boils down to a single value of true or false. So just applying a predicate to the front of the list predicates always return trues or falses. So that is a Boolean expression in and of itself. But if you like, I would say it is redundant, but you can say, is the result of this equal to true? If it is, do this. Otherwise, do this. Does that make sense?
Yeah, that makes more sense now. Thank you.
But in general, I would say you, at this level, you probably shouldn't be writing it like this. It's not wrong, but it is redundant. At this point, you guys should have a pretty good handle on Boolean expressions and resolving things and kind of wrapping your mind around, oh, this is already a Boolean. Can I work with it? But this says the same thing, so it's fine. Okay. That one felt like a half star, Brocker. Yeah, that was man. All right. Is it? Oh, I see. So list index predicate list returns a zero-based position. So this is like index of from Java. This effect we were running. So list index predicate list returns the first element, the position of the first element of the list that satisfies the predicate. No element in the list satisfies the predicate, then the list is called list index. It's having us return false instead of -1. Find list index to be a lambda that takes in a predicate and a list. Is that what it took? All right, and we'll have our standard if. So if null list, if I'm out of stuff, go ahead and return false. If I'm not out of stuff, we probably like the con better, right? Null list, boil down to false. If it's not null, then pred carve list. So if the pred of the carve list is true, then what will we boil down to? We're going to boil down to a number, right? Okay, well, where does that number come from? So we probably need to pass a number along here, or what we can do, let's see. Can I do something by just passing around ones and zeros? So I can say +1 for the index. Yeah, I think I do need to pass around a number. So we'll call this guy list index helper. And this guy will take in a pos. So if we found something that is equal to the predicate, we'll just boil down to pos and we're done. Otherwise, or else, we'll be calling list index helper again on plus pos1 on the same predicate and the coder of the list. And then we need to define list index. It's going to be taking a pred and a list, and we'll call list index helper. Passing it a 0, a pred, and the list. For example, number A213B7. Should give us a 1 for this one. There's our 1. Let's look for take the symbol out of here. Now we should get a false. I think that solves all of them. Look good. All right, question on this last one. So this is kind of another pattern where we needed to count. And as we whittle down our list, we're increasing our position to keep track of where we kind of mechanically are in the list. All right, so that is the solution to today's homework. Not too bad. All right, so let's look at what the next thing looks like. All right, so we can look at this. But by the way, this still does leave me open to this over the weekend here, Clancy, so still have to have good participation. We'll see what happens. All right, so 2*1, every. Going to take in a predicate in a list, returns false if any element in the list fails to satisfy the predicate, returns true otherwise. So this is going to be similar to what we just did, right? But we're ultimately going to keep doing trues as long as, well, let's see. So as this example here, is everything a number? This should be true if everything is a number, return false if any of the elements fail. So this one, the very first element fails, right? A fails, so the whole thing is false. Number for this other one, the whole thing is true, but if you maybe had a symbol sitting down here, you would have had, oh yeah, this satisfies, this satisfies, this satisfies, this doesn't, the whole thing is false. So the answer is either true or false with every. All right, so let's take about 4 minutes or so, try to solve this, and then we'll do it together. All right, so let's take a look at this guy. So our pattern is we want to process every element of this list. We want to ask a question about each of those elements. And if we ever fail that question, we're going to return false. As long as we don't fail, we're going to keep processing the next element, right? So that's our pseudocode. We just verbalize what we need to do. So for every, this guy is a lambda that's taking in a predicate and a list. And we will have a cond null list. And if we've run out of places to check and we're still kicking, we return a true. Otherwise, if the pred of the car of list is true, then we can't make any final call yet, but we're still kicking. So what do? We return whatever every returns, passing in the same predicate and passing in the coder of list. Otherwise, I failed, and I want to return false. So ABC 3E for number. Definitely not all numbers, so we'll get a false. 1, 2, 3, whatever. This should be a true. Those are true. All right, questions on that one? So we should be getting a feeling where these things are getting, even though we know the problems are kind of getting harder, the solutions are feeling easier because we're seeing the same patterns over and over again. All right, exists returns true if any element in the list satisfies the predicate, and false otherwise. Go ahead. Let's see, map. Well, what you can do is, here, let's look at map for this one. Define every to be a lambda, we'll call this every 2. To be a lambda that takes in a predicate and a list. And what we'll do is we'll map lambda x pred. Actually, we'll just map pred across the list. Let's start with that. And what that will do is it will give us a list containing a bunch of Booleans, right? So here's my list of trues. All right. Now, one thing we could do, I want to test something here real quick. What if I say and? And expects at least 2 arguments. So what I get here is this list. Is there any way for me to get a single true? I mean, map can give us something in that format that we can then process through and just and everything together, right? So I'm not sure that's really any better than we had before. So I mean, writing it with that, if I map this across there, I can then take the result of this and go through and just say, I'm going to and all of these Booleans together, and as long as they're all true, the whole thing will be true. So I could call this guy every 2 helper. This guy's a lambda that will take in a list. And what it'll do is it'll say if null list, then boil down to true, else we will and carve list with every to helper on the footer list. That'll and them all together. So then what we would do is we would call every to helper on the result of that map. That gives us our true or gives us our false. Yeah, I'm not sure that's an improvement, but it's a thing. Yeah, otherwise what you'd have to do is you'd have to find a way to take every map across that list, something that negates what's there, and then take the car of the result. And try to think, is there some function that will give me the there might be something weird, but nothing that's popping into my head right now. You know, I was gonna say, you know, if you can replace any true with nothingness, which will effectively then leave you with a list that if it has anything in it, it's false. Because you would only be left with the falses, let's say. So if you have anything, if you have the empty list, the whole thing's true. But if you have the non-empty list, then it's false. But I don't think map can give you nothing. I wonder, does a list with nulls in it, does that have a length? And I'm guessing if I ask for the length of this, I'm going to get a 2. There are 2 things in there, yeah. I don't think it's going to work out. All right, next one. Exists. Returns true if any element of the list satisfies the predicate and returns false otherwise. All right, so this one should be pretty similar, right? In fact, we should be able to take our solution to every. Well, actually, why don't you take like 4 minutes to do this one now that you've seen the solution to every to practice it. So this one says it should return true if any of these elements satisfy this predicate. Okay, so that means you don't have, as soon as you bump into one that satisfies it, you just return true. No more recursive calls. When you run out of places to check, you return false. If you find something it doesn't satisfy, you check the next one. All right, so let's take a look at this one. It's called exists. And that's going to be a lambda that takes in a predicate and a list. Cond null list. Go down to false. We didn't find it. Pred car list. Boil down to true. Else. Call exists, passing it the predicate and the coder of the list.
These parentheses are haunting my dreams already.
We get so much worse. It's going to be amazing.
I had the solution, I just didn't have the parenthesis wrapped around the hashtag T, so sadly.
Well, notice that it does, like as you're going through them, it shows you kind of where it ends. So if you see that parenthesis right there, it shows me that it wraps this production.
Yeah, it's just learning the syntax for me. It's just taking time, but we're getting there.
I got you. So if I switch this to symbol, symbol still exists, but then we'll dump the A. That should be true. And then we'll dump the A, and now we're false. Okay. So that's exists. All right, next one. Oh, this was a good one. So up. This removes a pair of parentheses from each top level element of a list. The top level element is not a list. It is included in the result as is. Have we done down already? Okay. So up, down are equivalent to the list. They undo each other. But down, up does not. So if we up the list containing the two lists 1, 2, and the two lists 3, 4, we end up with 1, 2, 3, 4. All right, so take a stab at that one. This one should be a little tougher. wonder if the sign they just put up on our door pertains to us. I'll walk over there while you guys are. Everybody out of here.
I wonder if that was a shield as well.
You just saw your shield and you had it on it.
Oh, no, teachers are allowed to wear shields up there as long as they're still there. I don't think students are allowed to wear shields without a mask, period. Yeah, that's not a made up thing. As long as the teacher's in the front of the class, they're allowed to just wear a shield. But I wouldn't be allowed to walk over there with just a shield. That's why I had to switch. I think I saw an email yesterday, maybe there was some from the provost's office, there was some teachers maybe telling students that once you were in the classroom and seated, you could take your mask off or something. I don't know. It's all very confusing. We can always do the driveway classroom or the parking lot classroom. You know there's one out there? Yeah, it's out here by behind the field house. So I think we can reserve that. It's a classroom. So they took up like half the parking lot there and put up a giant tent that you can reserve as like, I think they can hold like 50 people or something like that.
I haven't even driven past, like, I haven't even gone past that at school.
Oh yeah, that's where I park, right there. That way I just come up the stairs and I'm right here by the room. But yeah, so there's it's a big tent. Takes it, it's taking away a whole bunch of parking spots too over there. All right, let's take a look at this. So up removes a pair of parentheses from each top level element. Okay. But if it's not a list, then we leave it alone, right? So that's kind of the kicker on this one. So define up to be a lambda that takes in, so just taking a list, just a list, right? I'm taking a list, and what it does is it's going to go through this list. So we'll have a cond null list. Will boil down to the empty list because we are creating a new list, right? Our ultimate result here is we're creating a list. So we're probably going to be constructing something maybe with a little appendy curveball right in there. All right, so if we're dealing with the empty list, then what are we going to do? Oh, if we're dealing with the empty list, return the empty list. Otherwise, if list car of the list, if we're looking at something that is a list, how do we remove one level of parentheses?
But you have to go through that list.
You append the car of list to the entire.
Yep. So append car of list onto whatever up returns for the cooter of the list. Remember, the way append works is it glues these two lists together. So it will remove one layer of this. If that guy has lists inside of it, they'll still remain. Those are the elements inside that list, right? It just glues them together. So if I'm looking at a list as the first element, I need to do something to that list. So what I want to do is remove one layer of parentheses. And how do I do that? Well, I just append that list onto the result of the rest of it, which will naturally remove one layer. Else, it must be a single element, right? And if it's a single element, we will cons that element onto whatever up returns for the coder of our list. So 1, 2, 3, 4, so up. Oh, I did not give it accurate input. This was a list. Oh, hold on. Because I still give it bad input. There we go. And what's their other example? Yeah, it's got a list inside of a list. So up, X, list Y, Z. List, oop, X, list Y, Z, something like that. Is that it? Yep, so we unwrapped these elements, but kept the list Y. All right, so that is up.
If you use display when you're writing or calling the function, it gets rid of things like list when you call it. So
it's probably true, but I think it display shows you like it doesn't it put it like in a weird square or something like that, or you just like the look of that better.
I guess it just looks a little cleaner in my eyes, but that's just me.
Yeah, that's fine. I'm specifically not doing it because Clancy likes it. So
That's also fair. That's also fair.
all right, so does up make some sense? All right, so again, you see some of the patterns here. They're drilling you on append, knowing when to use that versus knowing when to use cons, because these things are going to come in handy when we start constructing our language stuff. All right, let's just see what this homework that Clancy is complaining about looks like. It's only 2 questions. Oh, the merge sort. Oh. So it kind of gets worse, right? It's like, please no homework over break. It's like, oh, well, maybe it'll be an easy one though. Is it really a holiday over this weekend? Does that count? Like, do people legitimately have plans? Do you
Yes.
have plans? Oh, hiking? Is that the hiking class? All right, let's just look at these for a second. Flatten returns a list of the symbols contained in slist in the order in which they occur when slist is printed. Intuitively, flatten removes all the inner parentheses from its argument. All right, so if we took in a list like this, it removes all the inner parentheses. What if I only give you flatten to write for Tuesday? And then we'll do merge sort in class. How does that sound, Clancy?
I don't know. It's a hard bargain.
just one question. It's one question. Because merge sort is rough. Merge sort done the right way is rough. There's actually kind of a cheat way to do merge sort that's horribly inefficient that isn't really significantly easier, but it's different. So for Tuesday, we will do just exercise 1.27. So, and this is actually homework. So we'll call this classroom example. And then for homework 4, we'll say just 1.27. We will do merge in class. All right. And we're done at 25 or 35? Okay. All right, so I'll go and put that up on Slack or on Blackboard. I will paste all the code we did from class today up on Slack. All right, any questions from the online folks? Going once, going twice. All right, I'll see everybody on Tuesday.
See you later.
Later.